Hello everybody, welcome back to Fastware. Today we're going to be talking how to ace your engineering interview when you're presented with the algorithms and data structures questions. So this particular example I picked at random. I've seen similar when I was doing interviews myself, but it's nothing special about this. So the problem space for algorithm and data structure questions is that you have two operations which are opposed to one another algorithmically, and you want to implement a correct data structures in order to solve this problem efficiently. So this particular problem description is to design a software system that receives sales of each vehicle from any country in the world. Each country may have up to 100 branches. The system should provide an API to query and branches which sold the most cars. The result set must be in the descending order. So again, we need to record something. It needs to be ordered, which that's where the conflict arises. So we need to also provide the algorithmic complexity analysis of our algorithms here. And we have a skeleton here. So record vehicle sale gets us a country code and a branch number and account number of vehicle sales at this time. And the get top branches, given that M value, we need to return that number of results back. So with that out of the way, let's begin, and we'll be talking about three separate implementations, sort of a naive implementation, which I would say somebody's just out of uni would go for. And then a developer with a 3-year of experience, that will be a second round. And the last one would be what I would say a professional software engineer who understands fairly decently the constraints of a problem and also data layouts and algorithms and whatnot. So with that out of the way, let's begin and implement this naive implementation. So for this particular implementation, we'll be using a map and a set. Map will be containing a pair of a country code and a branch number as its key, and an int to contain the amounts sold, so number of cars sold. A set will be containing a sorted list of our country codes and branch numbers. So again, we have the same country code and branch number as a key to the set. So we'll be implementing a set comparator since we need a very special comparison here, which involves comparing not only the amounts but also the country codes and branch numbers in order to ensure the uniqueness in the set. Otherwise, the items would not be inserted if you provide, for instance, the same volumes for different branches. If you only sort by volume, it will not be inserted. So here, what we're going to be doing is just starting with saying, okay, so we have a greater amount. We'll look up from our amount map for that left-hand side and right-hand side the amounts. We have the less key also. And what we'll be doing is comparing, so if equal amounts, then do the less key, otherwise greater amount. So that set comparator included as part of the set will do the trick at ensuring that all of our entries are unique. So now part of the record vehicle sales, so we'll be creating that pair of country code and branch number, and we'll be incrementing the count for that map. So here for set, given the same pair, we'll be erasing a value from the set and then inserting, so to keep our set sorted at all times. So to get the branch number, we'll compute the size, since there are no guarantees given that top will be less than set that we maintain. So we compute the minimum between those two values. And then what we'll be doing is continuing by iterating through our set by pulling out the begin iterator. and then continuously iterating through it and extracting the the country code and branch number from the set and populating the result. Given that pair as a key, we'll be extracting from amount map the volume. So here it is. That implementation is fairly trivial. I'll just make sure to update everywhere and then build and run the test in order to ensure that everything's okay. Okay, so that's completed. So what we'll do is do a little bit of data analysis and algorithmic analysis here. So given the record vehicle sales, so we have the amount map. We know to look up anything in a map, we have a log n algorithmic complexity here, since it's implemented as a red-black tree. So at worst, it's a log n if the entire tree needs to be rebalanced. That happens on insertions. So the updates would be a log n. So we can say amortized log n here. Now, for arrays and insert, we have a little bit of a bigger problem here, because while the set itself to arrays and insert is only a simple log n here, and if that will be all, the record vehicle sales would be the order log n complexity. It's not true, because the set compare actually pulls out the amount from the amount map, which is itself a log n. So in this particular case, for arrays and insert, both of these, the sets need to be sorted, looking up the amounts each time. So what happens there is that we actually do the log n squared, so order log n times order log n for both arrays and insert, pretty much guaranteeing to reshuffle the entire set twice, once on arrays, one on insert. So this particular implementation is constant factor of 2 log n squared implementation, which is not particularly great. But sort of a university level students might not know of that sort of a problem space here. So arrays and insert actually sorting everything. So particularly here, nothing interesting. So what we'll do is we'll copy our implementation and we'll implement something that a developer with about 3 years of experience would be expected to implement, at least from my experience. So we'll create the namespaces for it and we'll proceed forward. So what we'll do is, obviously we want to replace that constant sorting and looking up our maps. So we want to get rid of this. This is not efficient, and so we want to get rid of that. So what we'll do is instead implement a set item. So that set item will contain the country code, the branch number, and the volume. As so. So wouldn't you say that we're now starting to duplicate volume in multiple places? Yes, we are. However, we trade time complexity for storage complexity, since we no longer need to look up that map all the time. So what we'll do is implement a more than comparator and replace our set with our set item. So we'll do a similar thing as well previously. So we'll contain booleans for left-hand side volume greater than right-hand side volume for equal volumes. Then we'll follow with exactly the same for country codes. So we have equal country codes or less country codes, because we want to sort them in the ascending order, so by name alphabetically. And the last one is if the branch numbers are one less than the other. So what we'll do is, if equal volume, we'll do one thing. If not, it's a greater volume. So if equal country codes, we'll just return if it's a less branch number, otherwise less country codes. Now, to update our record vehicle sales implementation, we'll extract that pair into its own variable called CCBN, so country code branch number. We'll extract the current amount from the amount map given that pair. And then we'll create our set item. Our set item will contain country code, and will contain the branch number, and will contain the current amount. Given those values, now what we can do is go and erase our value from the set. Now, set still needs to be resorted, however, now we no longer need to look up, so that problem goes away. Following that, we update our current values and item volume, and then reinsert into the set, resorting it one more time with a new value. So the result, the getTop_n, is pretty much exactly the same. Now I'm just extracting everything from the set item. Right, so this is 3 years of experience, and we just need to include the greater amount, and then we can run and compare. So let's look at these two implementations. They both use a map and a set. There is nothing complicated between those two. However, one does a constant map lookup on every sort, and the other one does not. And the comparison between them are many orders of magnitude. So here we have 5 microseconds versus 75 microseconds, which is an insane difference between those two particular implementations. So let's have a look real quickly at what we have here. So we have the 3 years of experience implementation, which now finally contains the log_n for our record vehicle sales. So we have to pull out things from the map, to erase from the set and reinsert back in the set. All are order log_n, so we can say that algorithm is order log_n, and a constant factor m for actually getting our results. So that's pretty good. But now what we want to do is improve this slightly better. And I'm not going to be using anything much more complicated. However, I will be showing how to do this when you actually understand the problem well. So what is the key issue with this problem is we keep storing our country codes and all our values as strings, which tends to not go very well for us. So actually, we only need 2 characters. Country codes are 2 characters. So we actually currently have a string which is about ± 17 bytes. But we only need 2 bytes to store this. One for one for the other, and maybe even less. So we use 4 bytes to store values from 0 to 99, which is maximum of 100 branch numbers. We can do the same thing in 7 bits, which is less than 2 bytes, which allows to store 127 values. So particular volume is 32 bits, so that's not going to be changing. What we will do is start by implementing a hash value. So this is like a special type of key where we can actually store our values in a particular form. So what we'll do is store each character individually in 5-bit values. So 5 bits represent 0 to 31. We can store A to Z values here. And the same thing for the second character. Now, the branch number represents BN, can be stored in 7 bits, which store a maximum of 127 values. We have 0 to 99, which is good. So the max is 99 values. The last one is a panning, since actually we need to reach 32 bits here. We don't have enough. We basically zeroing out all 15 high bits to 0. Now all of these values in this union, that struct, represent a 32-bit value, which given the 5 bits and 7 bits, those 17 bits can store 131,000 maximum. So I just need to move it to correct place since I put it in the wrong place. So starting there. So we can remove our comparators, our items from a set since they're no longer needed. So what we'll do is implement actually a function to get this hash for us given the country code and branch number. And that is fairly trivial. So what we'll do is just initialize our hash value and then store C1 by doing country code 0 and then country code 1. The only thing that, so here we'll store the branch number. The only thing that we need to remember is to minus the A value, since A to Z is stored in a linear fashion, where those 31 values will meet that range. And then we're zeroing our padding and just return. So the set item, as we had before, will contain our hash value. But then what we also want to do is to contain our volume. And we'll follow exactly the same principle as above with the hash value. So we just shove this into a union. And what we'll do is we say that union between that struct and the uint64 is the key. So we'll use the uint64 as a key to the set. So now we no longer need to provide any comparators since these values are compared by themselves. So we store a vector of uint32 of volumes. That will be that size that we computed of 131,000. However, what we'll do instead is implement an init function to our algorithm, which basically resizes our vector. This is important since we'll be indexing directly each hash value having its own place in the vector. So now we no longer need to do a lookup here. So we'll do is hash value. We compute the hash value given the country code and the branch number. And then we'll use the hash value to actually index into our volumes. So here we can extract the current volume from the volumes vector. We can actually compute the new volume by adding the current volume and the count provided. And lastly, we'll just update the volumes vector to the new volume. So that is a one implementation. Very fast and very efficient. So what's next? We will be creating our set item. So we'll provide our hash, the current volume that we have. And then what we'll do is we will be extracting the set node from a set using an extract API. This is more efficient since we no longer need to reallocate memory for that node. What we'll do is just extract the node, update its volume, check if the node is not empty. So we'll be set item dot value, and we'll be providing the new key value for it, and we'll be reinserting the same thing. So that removes the deallocation and reallocation every time we need to update the value, which is the majority of our elements, and hence we can save quite a bit of time there too. So get top and get top branches is pretty similar. The only thing that we'll do is basically, given our set item, we basically extract our chars. So we say item.hash C1, we add that A since we minused it at the beginning, and we'll do exactly the same for a second character. Now, following that, we just need to do, so we'll be resizing our result in between, so we don't want to do multiple allocations here. Single allocation will suffice. And the other thing is the country code. We know it's only 2 characters, so we'll be just storing as chart2 instead of that string, which is very slow and inefficient and very big at the same time. So now we're going to be updating our country codes, C1 and C2, our branch number, just a little correction here. And the last thing is actually updating our volume. So cars sold is item.volume. So we've done, with not a bit of work, is just understanding the problem space well. We actually updated everything that we have. We have the init. The last thing is to write that init into our engineering input benchmark to initialize, and we can build and finally run. So we have some result sets, but what I want to do is just run this for a longer period of time. So we have some better data to look at and to understand the standard deviation and actually medians between these 3 different implementations. So let's run that and see what we have. So we have the naive implementation finishing with 84, so it even got worse. We have the 3-year engineer implementation, and we finally have our new implementation. So looking at this, we can see that we managed to implement pretty much the same algorithm. It's now twice as fast, almost twice as fast. Of course, the gap between the naive implementation and a developer with about 3 years of experience is massive. But if we're talking about efficiency, 2 times improvement between the 3 year of experience and actually experienced engineer is massive as well. So back to our complexities. So obviously we still have this sorting that happens to record vehicle sales, and that is log n, and to extract them is order n, so a constant factor here. Constant order m. And that is, I think, pretty good. There are some more complicated algorithms which allow to do this much faster, closer to actually order 1 for both. However, that involves a lot more code and to be a lot more complicated, and is very hardware dependent as well. So we're not going to be looking at those. I think this has been pretty good. If you have any suggestions or questions, if you think that I made a mistake somewhere or this is not good enough, if you want to challenge me, please do so. Leave a comment in the description below. And happy acing your interviews. Subscribe for more. And I'll see you in the next time.